Hey everyone, my name's Thomas Little, and I just want to do a few plugs before we get started on our video. You can reach me on Twitter at ThomasLittleDBA. You can reach me on Facebook, and make sure you subscribe to our YouTube channels. A lot of great videos coming out, and alike. So let's go ahead and get started on our video. Our focus for this session is really going to be on the database engine. And so we're going to get started in talking about three categories of the components of the database engine. There's the query execution, there's the storage engine, and then there's SQL OS. Now, the query execution layer manages the query optimization process. So it parses the SQL Server to ensure that all of your syntax that you're passing to SQL Server is correct. And then there's the query optimizer, which considers the different ways that your query could be executed. Now, on the storage layer, the main responsibilities are to manage how the data is both stored at disk and in memory, and it uses a number of different functions to do that. It uses the page cache, it uses the lock transaction management. It manages the methods, any locking, all the transactions related to your particular query. The last layer or section is SQL OS, and this layer provides the operating system the functionality to interact with SQL Server. And we're going to get into a later slide a little bit of history behind SQL OS. So let's dive into CPU usage. SQL Server has its own internal scheduling system that is separate from the Windows operating system, and they call it SQL OS. And what SQL Server does is it creates a pool of threads, and then those pools map to Windows threads when work needs to be done. And so what happens is, well, let's take this. Why did Microsoft do that? This abstract layer that we saw in our previous slide. Why not map directly to Windows threads? Well, that's actually the way it was designed before. But what SQL Server wanted to do when it started getting into the operating system, the Windows operating system, was try to customize it a little bit so they could take better efficiency of the processors. Well, the Windows operating system's team developed Windows so that all applications could be developed on it, and they didn't have to worry about CPU management or CPU usage management or thread management. They didn't have to worry about that. So they wouldn't customize it. So what SQL Server did way back in 7.0, it used to be called UMS, created this very thin layer of the basically OS, very minimal subcomponents. All it needs to do is run. And then those threads map to Windows threads. So that SQL OS actually manages all of the CPU usage and then just utilizes the CPU on the Windows side to actually get its work done. That allows SQL Server to customize how it uses the work threads any way possible. You can't talk about CPU usage unless you're talking about parallelism. Now, SQL Server executes queries in sequential plans on a single task, and to reduce the overall execution time, sometimes what SQL Server will do is decide to distribute those queries over several tasks so that it can execute tasks or execute much faster. Now, parallel execution plans are only considered on very expensive queries, and that query optimizer decides whether a plan should be used based on two different aspects, and that's the max stop aspect and the cost threshold of parallelism. So what is max stop? It's a value that determines the limit of how many CPUs can be used in a query. So if you have a 16-core system and you set your max stop to 8 when SQL Server decides that it has an expensive query and it needs to distribute that query across processors, it's going to look at this option, this max stop option, and decide how many processors it can actually use. Now by default it's all processors, so this setting has to be set manually. Now the cost threshold determines the cost that a query must meet before a parallel query can be considered. So you can set this option and it looks at this along with MaxDop to determine, should I, with this very expensive query, execute it across all my processors, how many processors, and when do I start executing? So you can't talk SQL Server without talking memory. And I'm going to be honest with you, the more memory you give SQL Server, the happier SQL Server is going to be. So the main memory object of SQL Server is actually called the buffer pool, and it's divided into 8K pages of the same size within the database. And the buffer pool is made up of three sections. It's made up of the free pages, the stolen pages, and the data cache. Now, free pages free pages are pages that are not used yet and are kept to satisfy new memory requests, right? Stolen pages are pages that are used by other SQL Server components such as the query optimizer and the storage engine. And the data cache are pages that are used for caching database data pages. So all data operations are performed in the data cache. And if a query wants to select data from a specific data page, that data page is then moved into the data cache first, and then data modifications are only ever performed in memory. So what happens is you do a select or a data modification, it goes and grabs the page, that 8K page from the database. It then loads it into memory. You get your results if it's a select statement from memory, and if you're making a change, you make that change to the data page at memory, and then it flushes it out to disk through its own internal system, usually through a checkpoint. So why is that important? Well, disk I/O is actually really expensive, and if you continue to hit the disk, you're actually spinning that spindle or moving that spindle all over the place. So SQL Server utilizes memory because it is much faster than disk to retrieve data results and make data modifications for you. So memory is vitally important. You want to make sure that you have enough memory in your system to manage your workload. And that's another key thing that you have to be mindful of, is what your workload is. There is no default setting for memory. There is minimum requirements and recommended requirements, but it's always going to be, what is your workload? What is your workload like, and how much memory you need? Another very important part of SQL Server is I/O, physical and logical I/O. So what's logical I/O? Well, logical I/O is when a task can be retrieved from the data page, or retrieve a data page from the buffer cache. So it's when it doesn't have to go to disk, basically, to get its data. It can go right to memory. What's physical I/O? Well, it's exactly the opposite. So when it can't find its data page within memory, it has to go to disk. It then takes that data page, loads it in memory, and then serves it to you. So those are really two differences. Here's the big thing. You want to try to minimize physical I/O as much as possible. So how do you do that? Well, there are a couple of ways you can do that. You can provide enough memory to your SQL Server, to the data cache. That's one way of doing it. Another way is to optimize physical and logical database layouts, including indexes. So some indexes are vitally important to how you select data and alike. And you can optimize queries to request as few IOs as possible. So you have to tune your queries to target the data that you're looking for. One of the big practices that I've seen is sometimes developers and non-SQL enthusiasts will go out and say, give me all the data and then I'll figure out what I need. And so I always tell them, well, do the opposite. Figure out what you need first, and we can construct a query to get just that data. Because if I pull all that back, all right, it's going to pull all of that into memory. It's going to use all of my memory cache. It's going to push other things that are accessed in memory frequently out because it's such a large data pool. And then those other queries are going to get slow. So let me know what you want first, and then we can design your query for that. That's always vitally important. So you want to try to reduce as much physical I/O as possible.